guess before we continue our previous exploration, let me check this first. Okay, so previously we are trying to, what is it called? To check for the integer overflow with count, which is, let me open this, struct alpha, okay, count this one, which is an integer, right? And we use this stack overflow answer as a reference, and it looks like we can replicate the, what is it called, the integer overflow, but I feel like rather than hardcode this to 31, because again the author of the answer assumed that integer always 32-bit, so I want to try this mechanism, I guess. Let's try that out. Well, you can just open GTP like this, and wait a minute. Okay, let's just open this here. Start in max. Right, if we increase this, become 1, but if we, let's say, okay, this is, I think, y, let's check this, 32, right? This one, I think 31. Okay, that's why we use right shift 31, because the maximum is 31, I guess. Okay, now I'm trying to check this one. Before long, I guess, let's take a look at, is this, isn't this the same? Well, let's use this instead. I mean, like this one. Printf. Name.age. What is it called? Max, I guess. And we compiled it. Holy, okay. Okay. Oh, interesting. Name.age, okay. Okay, how many? 63. Alright, Now, the interesting question is that how long is long max? Wait, I think we need to do this. Holy. It's the same. Interesting. Print size of 4. And also 4. Long. 8. Okay. Now let's try this one. Print. No, not that one. This one, okay. And then size of, I guess, long. Multiplied by 8. Cut this one. Okay, but long. 0. Okay. Alright. Alright, now put unsigned. Okay. Size of unsigned. Interesting. Wait. Size of 4. Interesting. Yeah, of course. The question is that yep. Okay, let's add the information then. Okay. Size of value count. value count equal guess bit, no, not bit. I think they're bit, right? And then negative 1. Main debug. GDP scripts. Okay. Print. Right, I should break your tails. 60, no, 36, right? No, 69, size of value count. Non-pointer value. Oh, right. Okay. Yep, I kind of forgot. It's not a pointer. Da-na-na-na-na-na. Da-da-na-na. No. I think this gonna make it harder to Maybe I should do something like this. Declare. Alright. Limits. Okay. GTP scripts. Utils. And line 37. Okay, so run. No, 69. Value count. Wait. Okay. Oh, wait. Right. Continue. Okay. Letter overflow. And also mechanism only tested on the, what is it called, integer, not integer. So this method, okay. This method might not for the overflow value is defined. Let me go to the toilet for a bit. Right. Refactor utils. Size of what? Wait. Oh, okay. Not 31st. I mean, from our testing, right? Set this one. Size of long multiplied by 8 and then -1. Okay. It's still non-zero value. Okay. What is it called? Safe right. The operand for for safe right bitwise operator with this is assuming that we use integer that always 32-bit. The possible problem is when we change the count type to another type. Like long. Instead of in. That in mind. Let's try using size of to get the size value. The count value and calculate from that. The count size. We also using the bit because the bit just in case some system have more or less than 8 bits in one byte. Again, 33 utils. Okay, run. No, 69. What is it called again? Print value. Okay. Alright. Wait, it should be this one, right? Okay. And then continue. Okay. Okay, now let's try okay. Let's try checking this again. I'm still curious about this one. Okay, splice. Okay. case, let's try checking this out. Their identifier, their name, does not need to care about the physical address. Okay. For a C++ program, a succession of let me copy this in the chat in case anyone wants to see this. Okay. For a C++ program, the memory of a computer is like a succession of memory cells. It's 1 byte in size and it's with a unique address. Things are altered in a way that allows data representation larger than 1 byte to occupy memory consecutive address. This way, its cell can be easily located in the memory by means of its unique address. Okay. After the cell with address, okay, that's the one with cell. I'm kind of curious. What happened when we use integer, I guess. Okay, let's compile this. Case price. Okay. 94. No, 96, sorry. 96. Okay, interesting. Oh. Okay. This is the representation of pointer in long integer. Interesting. Size of 20. I mean, if we add 20, then yeah, it become like this, right? So when we write a pointer plus number in pointer arithmetic, what's happening is a pointer plus means of, okay, of the pointer type, okay. I mean, number. Is located in the memory by means of its unique address. The memory needed to store its value is assigned location in memory. Its memory address generally is left to the environment where the program is run. Okay. Generally, an operating system that decides the particular memory version on runtime. However, it may be useful for a program to be able to obtain the address of a variable during runtime in order to access data cells that are at a certain position relative to it. The test of hello, welcome. Let me copy this in the chat in case anyone want to see this too. Okay, address of operator. Okay, the address of by preceding the name. Okay, this would assign the address of variable my var to foo. Okay, this variable my var to foo. Okay, address of operator. Alright, we are no longer assigning the content of the variable itself to foo, but its address. Its address, okay. The actual address of a variable in memory cannot be known before runtime. But let's assume, in order to help clarify some concept, that my var is placed during runtime in the memory address, this one. Yeah, the ampersand, the address of operator. Okay, in this case, consider the following code fragment. We have my var 25, and then assigning the address of my var to pointer foo, right? But in this bar variable, we assign the value of my var to bar. The value contained in its variable after the execution of this are shown in the following diagram. Okay, right, this is my var, and then when using ampersand, we assign the memory address instead of the real value of my var in the foo variable, but in the var we assign the value itself, which is 25. Okay, first we have assigned the value 25 to my var. Okay, right, we assume the memory address is 1776. The second statement assigns for the address of my var, right? We assume 1776. Finally, the third statement assigns the value contained in my var to bar. Okay. This is a standard assignment operator. Okay, the main difference between the second and the difference of the address of operator, the ampersand, right? The variable that stores the address of another variable, like foo in the example, is called a pointer. Yeah, value assignment is standard. Okay, it's called a pointer. Pointers are very powerful feature of the language that has many uses in lower level programming. Okay, we'll see how to declare and use pointer. The reference: a variable which stores the address of another variable is called a pointer, right? A pointer are set to point to the variable whose address they store. Okay. An interesting property of pointer is that they can be used to access the variable they point to directly. This is done by presetting the pointer name with the reference operator. What is it called? Star symbol. Is that it? I usually call it star symbol. But yeah, this is the reference operator, not the multiplication one in the arithmetic operator. Okay, and they can be used to access variable they point to directly. Value point to by. Okay. I haven't tried closure yet, so that is interesting. Using the add symbol. Okay. Yeah, in C we use the star symbol for the reference. Is atom the same as pointer in closure? Interesting. Okay. The operator itself can be read as value pointed to by. Oh, not exactly. Okay. Yeah, I'm not really sure about closure yet. I haven't tried. Okay. Therefore, following with the value of the previous example plus equal star foo, the reference foo, I guess. This could be read as plus equal to value pointed to by foo. Okay. And the statement will actually assign the value 25 to base, right? Since foo is 1776 and the value pointed to by 1776 would be 25. Okay. This is the diagram, right? Okay. And then we assign this to bus. It is important to clearly differentiate that foo refers to the value 1776. Okay. Foo refers to the value 1776, while star foo, right, with an asterisk, sorry. Yeah, asterisk symbol, right? Asterisk symbol preceding the identifier refers to the value stored at address 1776, which in this case is 25. This is the difference of including and not including the dereference operator. Okay. bus equal to foo, right? Bus equal to value point to by foo. Okay. The reference and dereference operator are thus complementary. Okay, this is address of operator and this is dereference operator. The asterisk symbol. Okay. And can be read at value pointed to by. Okay. Thus they have sort of opposite meaning. An address obtained with ampersand can be dereferenced with. Okay. Earlier we performed the following two assignment operation. Okay. After these two statements, give true as result. Okay. Alright. Address of my var, right? Foo storing the address of my var. And then this one should be this one. The first expression is quite clear, considering that the assignment operation performed 25. This one. Okay. The first expression is quite clear, considering that the assignment operation performed on my var was my var equal 25. The second one uses the address of operator, right? This one, which return the address of my var, which we assume it to have the value of 1776. That one is somewhat obvious since the second expression was true and the assignment operator performed on foo was foo equal address of my var. The fourth expression uses the dereference operator that can be read value pointed to by foo in this case, right? The dereference operator and the value pointed to by foo is indeed 25. Okay. So after all that, you may also infer that for as long as the address pointed to by foo remains unchanged, the following expression will also be true. Declaring pointer. Okay. Wait, let me go to the toilet first. I'm back. Okay. Let's continue with the ability of a pointer to directly refer to the value that it points to. A pointer has different properties when it points to a chart than when it points to an int or float. That directly refer to the value that it points to. different properties okay, once the reference, the type needs to be known, and for that the declaration of pointer needs to include the data type the pointer is going to point to. Right, the type needs to be known, and for that the declaration of a pointer needs to include the data type the pointer is going to point to. The declaration of pointers follow the syntax. Okay, right. Where type is the data type pointed to by the pointer is not the type of the pointer itself, but the type of the data the pointer points to. Okay. Alright, the data the pointer points to. Right. Number pointer in. Okay. Character pointer char. And this one also the same, decimals pointer to double, points to double value, I guess. Yeah, I guess character decimal. Yeah, I think that is more less confusing. Would be easier to understand, right? Okay, anyway, let's continue. These are three declarations of pointers, right? Each one is intended to point to a different data type, but in fact all of them are pointers, and all of them are likely going to occupy the same amount of space in memory. The size in memory of a pointer depends on the platform. Okay. The size in memory of a pointer depends on the platform where the program runs. Alright. Nevertheless, the data to which they point to do not occupy the same amount of space nor are of the same type. Okay. The data to which they point to do not occupy the same amount of space. Alright. I think this is called. Let's try this one. Something like this, right? Size of in. I think char is 1. Okay. And what is it? Double. Let's check. 8. Okay. And when we use, let's say, char pointer like this, it is 4. Right? Okay. So this is what this statement is, the amount of space, right, to store the data, like storing integer, char, and double, not the same. Point to an int, the second one to a char, and the last one to a double. Okay, therefore although these 3 example variables are all of them pointers, okay, they actually have different type. This one, right, respectively, depending on the type they points to. Okay. Note that the asterisk use when declaring pointer only means that it is a pointer. It is part of its type compound specifier. Okay. Type compound specifier. And should not be confused with the reference operator. Right, I think this is, what is it called? This confusion might happen, right? Because we are using asterisk too when declaring a pointer. I think some people make confuse like this, right? In PTR, let's say 1, let's say A, something like this. And this is actually the reference, as far as I understand. We have the reference the pointer PTR and assign, let's say, a new value 69. Is used into context, declaring a pointer variable, and second, it is used to the reference. Right, that's right. When I first learned C during the early live streaming session, I got confused, like, is this one declaring a pointer or the reference, right? Because we put using the asterisk symbol. This one declaring and assigning the, what is it called? The memory address, right? For the pointer to use. And this one, it turns out dereferencing the PTR pointer. So let's say if we do this, right? If we are doing this, we will get an error because we have no idea what's in the PTR pointer, right? What is the value in the PTR pointer? And the error when the dereferencing here. So we might dereferencing a memory address that we don't have access or might not even exist, So I kind of get the confusion with the reference operator because I've experienced that. Like, what does this mean? Is this dereference or declaring a pointer? Right. Okay. So and now I right in pointer PTR and then assign the address of edge to PTR, right? At first I think that we can do something like this, like directly assign, or maybe like some memory address, something like that. And maybe like this. Oh no, yeah, like this. This would cause a segfault. The value of x, right? Okay, the value of x, so written with an asterisk. They are simply two different things with the same sign, right? So yeah, for the new user, I guess, be careful of the asterisks. The context matter, how we use the asterisk, right? Okay. My first pointer. Oh, okay. I think this is C++. Right. I'm learning C from C++ tutorial. You declare the pointer, right? Oh, okay. Yes, this is the problem, right? Because we are not sure what's the value of this pointer, the PTR pointer. So we need to give it the assignment, let's say A, something like this, right? This will work. But if we didn't give the assignment, something like this, and we are trying to change the PTR points to, the value that the PTR points to, yeah, we will get in trouble. Because we have no idea what's PTR points to, you know. Okay. Right. Yep. I mean, in the beginning I didn't understand that. So I got a lot of segfault. But now, yeah, I'm slowly understand how this works. Okay. This one, right? We give an assignment to the pointer, to my pointer, right? And then we change the my pointer value, not the my pointer value, the my pointer points to value, you know. And I guess this will also change the value of first value. Right? So yeah, this is actually variable. What is it called? Variable is one way to create a data storage, I guess. Right. I've made a blog post to make it kind of easier to understand about pointer in C, in case anyone wants to see this. So I think pointer as a warehouse, you know, like we have the warehouse key, the pointer itself, and the keychain with warehouse information on the key. See, the warehouse as data storage or the memory, right? And then the warehouse key as the pointer in C. And the keychain is actually the memory address that we save in the pointer. So when we try opening the warehouse, I give an analogy as a referencing a pointer. So, and then we got something from inside the warehouse. This is the, what is it called? The example that I give, right? Let's say we have a key, but we don't have the keychain or the information about where this key leads to, right? How do we know which warehouse we are supposed to open? Nah, and this will confuse us, right? Which door do I need to open with this key? In computer, kind of the same, I guess. See, we are trying to put 69 into the warehouse, but we have no idea which warehouse should we put the 69, right? So yeah, this is what is it called? To make understand pointer easier, I guess. the warehouse analogy, like there is key and there's also keychain, which which come along with the key, and then when we want to, let's say, access the item in the warehouse, we take a look at the keychain. Oh, this is the warehouse number 3, for example, and then we go to warehouse number 3, opening this warehouse using the key and getting something from there, right? I think in my mind, when I'm working with pointer, I usually use this warehouse analogy. I mean, it helped me understanding the pointer better, I guess. But yeah, everyone might use different analogy. Okay. Right. Okay, let's continue this. Oh. Wait, let's take a break first, I guess, before continuing this. Don't forget to drink water. Okay, for those who just joined, why I'm trying to learn about pointer is actually because of this challenge, this key splice pointer challenge. Let me copy this in the chat in case anyone wants to check this out. So this is actually quite interesting, right? So we have this x as an array of integer with 5 elements, right? And then we have this line, print the pointer of x, which as far as I know will print the memory address of the first element of x, right? And then this one, okay, let me show this instead, I guess. So this is from the previous session, right? Let me run this playground case price. Okay. See, when printing x, it actually the same as this expression, right? Address of x index 0. Okay. Actually the same. And then this one, x plus 1, the memory address, right? It's actually the same as this one. Address of x index 0 plus 1, right? Or in this case is address of x index 1. Okay. And this is, I guess, the representation of memory address in integer that I recently tried out. This one, LT. Yeah, I'm using long type instead of the usual integer type, just in case it will have more value than the maximum integer value. Okay. this is I'm kind of understand, right? Like it is the next, what is it called? The next memory address. See, this is 32, this is 36. And why is it 4 difference? Because in my system the size of integer is 4, so we increasing the memory address by 4, I guess. And then 40, 44, 48. Now the interesting part is when we use this, no, not this one, this one, the address of x without specifying the index, this one. When we use like this, we will print out the address of index 0, right? Like this one. But the interesting part is when we add one number, this is the interesting one for me, at least. What happened? Right? Why is it like different? Address of x plus 1 and x plus 1, even though the address of x without the index 0, right, having the same value. I think that's quite interesting. So yeah, I'm trying to figure that out. Why is it like that? And from this Stack Overflow answer, okay, 20 pivot it and record. The number you are adding to the pointer will be multiplied by the size of type that the pointer is pointing to. Okay. For example, if you have a pointer to an int and an int size is 4 for byte, pointer to int plus 4 will evaluate to a memory address 16 byte. For ints ahead. Okay. So when we write a pointer plus a number, a pointer, a number multiplied by the type size, I guess. If this is int, then yeah, this is the size of integer on the system. Now, why, I mean, we have this, right, the 20, the size of x, which is array of 5 integer, the size is 20, so is it also like the same? Like maybe this one adding by 20, something like that. Yeah, I'm still not really sure. That's why I want to understand more about pointer. Yes. Array address of array x, then it points to the base address of array, the first index. Okay, base address of array, the first index. Okay, therefore when we increment 1 in that base address, the array of, okay, wait a minute. Okay, let me change something real quick. Okay. Let's try this. The address of x as a pointer to the entire array, which means when we increment by 1, it increases the size of entire array, that is 20 bytes. Okay, pointer points to the entire array. Oh, okay. And increase the size of entire array, that is 20 bytes. Points to the entire, points to the entire array. Okay, it is point to the entire array. Franz Sharma, can you, I think yesterday you want to send a reference, right, about this one. Can you send the URL again? I'm trying and see if you can send a URL in the chat. Okay, maybe I will pop out chat. Okay, this one. When we use the name of array x, it points to the base address of array. It is the first index. Let me hide this first. Okay. When we use the name of array x, then it points to the base address of array, which is first index. Therefore, it will increase the variable of the array O. The memory address, the address of x, a pointer points to the entire array. Okay, array, which means when we increment by 1, it increases the size of the entire array. Increase the size of the entire array. is 20 bytes. That's why. Okay, when x plus 1 increase the size of entire array. Okay, so does this array memory address arithmetic, I guess. Is this what happened? Like a pointer, right? A number 1, the number is 1, multiplied by size of a pointer. Wait. Let me check in GTP, I guess. Without matching. So let's say we have this. Increase the pointer by the size of the array. Oh, increase the pointer by the size of the array. Oh, so okay. If I understand this correctly, right? Let's say we have this. No, not this one. This one, I guess, right? And then we are plus by, what is it? A number multiply size of. The number is 1 multiplied by size of, let's say, the pointer, size of x. Is it something like this? I mean, assume x equal this one, right? Why is the programming language still rules? Manipulation and non-location. Wait, okay. Oh, okay. In C, array address is equal to its value in C. Okay. Okay, we have char, right? Some cool string. Okay. My array. This is. Oh, it is called scaling factor. Okay. Yeah. Wait. C programming scaling. C programming scaling factor. For pointer, I guess. Alright. Let's see if I am a robot or not. The moment of truth. Okay. Still, like what? Okay. Am I a robot? Yes. Oh my god. Bear with me, everyone. Okay. Oh. Yeah, this is hard decision. Oh my god. Okay. Well, let's check with another search engine. The programming scaling factor. I mean, yeah, it didn't give. Alright, let's try this one more time. This is the bus. It should be right. Oh, wait, did I miss the bus? Oh my god. I think I am a robot. Yep, bicycle, okay. This one bicycle. The event selection in CAPTCHA. Oh, wait, event selection. Wait. Okay. Scaling factor. Oh, is this the one? 4 or 6 block. Oh, okay. I didn't know about that. I guess, well, we learn something new every day, you know. Thank you. Maybe I will try that next time. The event selection. Okay, that is interesting. Is this what you mean by scale factor? To shape similar shape. A scale factor 3 means that okay, wait. Let me check this first. Oh, wait. Let me check this. Since early reference decade to pointer between R and okay. The type R is a pointer of type pointer to array of T to the entire array. A pointer to the entire array, okay. In ANSI, the ampersand in ampersand R generally elicit a warning and was generally ignored. Okay. Under ASCII compiler, okay. I think let me copy this in the chat in case anyone wants to see this too. Under RC compiler, a simple reference to an array, it's a pointer of type pointer to t. The array face element. Okay. Reference A has type to and has type pointer to int. Is a pointer to array of 10 ints. Okay. Oh, okay. The entire array, alright. Let's check. Wait a minute. Declared as the. So according to your declaration, that is 10 byte because n is defined as 10 and size of this one is an address of an array and the size is 4 byte on the ampersand str2 is also the address of the first element. The following diagram. Okay, let's check this one. Okay, str2 plus 1. Okay, assuming str address start from 201, 10 char long. Alright, partially initialize. At an initialized position, str2 index. Okay. Oh, this one. Okay. Alright. The location of 200 is unallocated. Having garbage value, access to this location is illegal. Define behavior. Okay. Because n is 10, right? 1, 2 until 10. The one who didn't have the value will have this null terminator or zero terminator symbol. Okay. For the above diagram, we can write code like this. Code bad. Wait. Let's see. Am I lagging? I hope not. Okay. Notice that at first line, the output address differ by 1 byte. First line, okay. By 1 byte, right. But in the second the difference is 10 bytes. Is the array's pointer as shown in the diagram above. Okay. Alright. In the diagram above. Okay. A pointer like this, when we add 1 to a pointer variable, it starts to point to the next element of its own type. Oh, okay. For the 10 byte difference, because str2 is an address pointing to an array. The 10 bytes difference is that to points to the next element of its own type. So let's say we have 5 index, what is it called? Array of oh, hello, Purpose, Brain, Foxfire. Oh, you have some experience with Python and just start learning C. Yeah, I mean, I want to learn C, right? So why not learning C together? That's why I do this live stream. Which means that what I say might not be correct. Because I'm also learning, right? I mean, I'm trying to put up some experience myself, Okay, first, Sarma said that storage class initialize the variable if programmer leave it uninitialized, and a partially initialized array fill the remaining uninitialized element with 0 value. Alright. Yep. And a partially initialized array. Okay. A partially initialized array element fill the rest of the element with 0 value. Right. For those who just joined, the Van Sarma explaining about this one. Right? We define n as 10, right? Using the macro here, and then we use 10 in here, which basically means that we have array of 10. The element of the array is 10, right? But we didn't specify the rest of we only specify 5 for the char, the character, right? And that is why this is filled with the 0 value, until 10, because we define n as 10, right? So the next one, which is 11, right, is actually some random value or something like that. Okay, this is the one, right? Okay, where is it? I think this is it. Notice that the first line, the output of address differ by 1 byte. Is it this one, right? Differ by 1 byte. But in the second, ASCII, okay, in ASCII 0 equal backslash 0. Okay. Oh, I mean, do we have like another character set other than ASCII? Like I only know about ASCII, so maybe there is another character set other than ASCII. that would be interesting to check out, I guess. Notice that at the first line, okay, 1 byte, but in the second, this one, right, the difference is 10 byte. I mean, I didn't know how to read this yet, like how is this 10 byte different, right? But if we print out as an integer, like this one, I think the difference is easier to understand, I guess. This is 32, right? And this is 34. Why is it like this? Because the size of int is 4, so we take up 4 bytes. Or because of the integer value, right? This is 44 and this is 48. Now, what I'm kind of trying to understand is this one, the $x plus 1. Like, as you can see, it is different from the x plus 1, right? Okay, wait. Let's go back to this first. Hold on a minute. Let me go to the toilet again. Be right back. Alright, I am back. Okay, let's continue. A sound in the diagram above. Okay. According to the rules of the pointer arithmetics, when we add 1 to a pointer variable, it starts to point to the next element of its own type. Okay, so from this, what is it called? From this statement, the next element of its own type. So does that mean when we have array of 5 in, right? When we add 1, for example, plus 1, it start to point to another array of 5 ins memory address. I mean, like and then the next one is another 5 in and 5 in. Is that it? That's why, what is it called? We use the size of the array, I guess. Interesting. We're not giving the first element. By doing this, we can access the first element, whereas this one will not give you the first element. Instead, it will give the address of the first element. Oh, interesting. Alright. I mean, I kind of know about this because array decay into a pointer, right? So basically it is like writing str to this one, right? I mean, we can try that out, I guess. So I use this one, char. Okay, we are building a new line like this one, the empty new line. Okay, and then printf this one. Let's use the integer format specifier. Okay, and then x. Did I have this? Yes. Okay. Case price pointer challenge. Okay. 0. Oh, interesting. Yeah, because we haven't initialized the we haven't not initialized but assigned the value yet. Let's see. Let's try something like this. No, not this one. Compile this, and then what is it called? Case price. Okay, 69. Right. And then let's try out this one. Right, something like this. Okay. Okay, playground. This is called. Is it because of this one? Let's find out. Case price. Okay. Okay. This is the ASCII. What is it called? ASCII table. this one. The 69. Where is the 69? This one. 45. The hex number of 6945. But yeah, let's try to find the one. Am I liking? I see table for numbers. For whatever reason. Okay. Yep. Let's find another one. This one. 69, right? The hex value of 69 number in the ASCII character set is 45. That's why this is 0x45. And this is, well, yeah, I think this is the memory address of the first element. Okay, wait, let's try this one with the double asterisk, right? Now we get the same value as this one. That is quite interesting. Okay, oh, let me copy this in the chat in case anyone wants to take a look of the ASCII character. Okay. Wait, is there something that I can... Oh, okay. Written for byte. Okay. Test of an array. Okay. So this one print out the size of the pointer, right? Other than the size of the array. Okay. Okay. Third difference. Alright. Equal to this one. And value is address, okay. And hence, oh, equal to this one. Value is 8. It's an array of type char, okay. And output are stored in memory. Oh, this is right. This is more about the string literal and character of char. Okay. Right, basically as far as I understand, for those who just joined, string, I think this one, right? Yes, this is the one. As far as I understand, the string literal is saved in another, what is it called? Memory, another type of memory, a read-only memory, something like that. So let me run this to show. Not this one. Literal. Okay, this one. Right. Okay. If we can see, as we can see, the str1 is actually inu, right? Which have this memory address, and the str2 is actually changing the string with itu, right? itu, and it have this memory address. And now we are trying to change the string again with enu, right? And surprisingly, we have the same memory address as the str1, right? So it is kind of changing the pointer, I guess, for the string literal. And then when we, what is it called, change to another string literal with double quote, adding two more character, right? We are using different string. We are using different memory address. So I think this is kind of interesting. Oh yeah, for those who want to check the progress, you can check in this GitHub repo, I guess. This playground, you can check out. I've made quite a few of the playground file for the experiment, right? Maybe you want to check this out on your local machine or something like that. Okay, that is a little bit about the string literal. Okay, so this is more about the char and string literal, and quite interesting. Okay, let me copy this in the chat too. For those interested in this, let me remove that. Okay. The name of an array usually evaluates to the address of the first element of the array. So array and have the same value but different types. Okay. And okay, does that mean, I mean like this one, you know? Let's say we have, what is it called? Let's say this is memory address 1 until 5, right? If adding 1, right, mean that we are printing the address 6 until 10, for example, and then printing again the off by 5. Is that what it means by different types? So that is why when we have this array plus 1 is different with address of array plus 1, because this is the first element, right? Not the entire array, but this one is the entire array and off by the size of the array. So this might be 11 until 15, I guess. So 5 integer, 5 integer, and 5 integer. Is that how it works? Interesting. And in our case, right, because the size of integer is 4, let me run this again. Because the size of integer is 4, like this one, right? And we have 5 elements, so we are off by, 20 bytes. Am I using qtime as TE? No, I'm using i3wm as window manager, 3wm.org. I'm using this one. Copy this in the chat. I'm using i3 window manager. Okay, so let's I guess explain this. Okay, this is kind of interesting. And well, where should we explain this? Integer value, okay. Things in this one, right? By adding one in one, we are adding by the size of the array. For example, when we have array of 5 integer and we add 1 to with x plus 1, we will have the value of by 5 integers. The representation would be like this: 5 in, 5 ins, 5 ins. is what? This is x, I guess. And then this one is x plus 1. X plus 2. Is this the correct representation? Like 5 in, 5 in, 5 in, right? Off by... I don't think... Maybe... yeah. 5 plus 5 in. In and then another 5 in and then another 5 in. Maybe let's say the memory address of is 001, right? What is it called? The representation would be representation would be 01 until 005, I guess, and then 006. Oh, right, in, right. And we have one byte to make things easier to understand, right? We have one byte. Now that make me thinking, maybe we should use array of char instead of array of in. With one byte of, what is it? 1 byte of arrays element, something like that, I guess. Okay, and then 0, what 0, okay, something like this, and then this one 12 until 17. Okay. Yeah, this make me realize maybe we should use char character instead. Char, no, yes. Oh, except for this one. Let's compile it again. Hello, welcome. Teacher's code. I'm trying, oh yeah, for notice would just come. I'm trying to understand this expression, like why is the %x plus 1 is different with the x plus 1. Let me copy this to the chat in case anyone want to see that too. Please. Okay. Yeah, it is nil. A and B, right? Let me compile this again and guess price. Okay. The size of char is 1. Okay. This is the pointer, right? Okay. This one, see, 67, 68, 69, 70, 71. Okay. And because of this, right, we start at 3 and we have 5. Okay. So this is the next one. Adding this by 1. And yeah, this is equal to the the index 5 memory address, right? Okay. Yeah, but then I need to change this. Not 5 in, but 5 chars, 5 character. Char, okay. 5 char, okay. The first one, and then the next one is this 5 char again. The next one is 5 char again. Like off by 5 char. From what I understand. Right? If you look at this one, 70, and then this one is 72, right? And then off by 5 char again, 77. Okay, I think I set the memory address off, and we have one byte of arrays element. 001 until 005, 006 until 011, 012 until thank you. I mean, I just want we to learn together. So whether you like this or not, it is not really it's the secondary part, it's not the primary goal. So okay, this is interesting. 006, 0011. Okay. Okay. And then what is it? Scale of 3. Da, 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 da. String copyright. Oh, there are two exceptions to this. When the array name is an operand of size of or array, okay. The name refers to the array object itself. Thus, size of array give you the size in bytes. The size in bytes of entire array. Oh, okay. We are talking about the size of, right? Or on array, address of operator, the array object itself. I'm kind of curious, like I've tried out this one, right? Because array decay into, what is it called? Into pointer, right? When we actually having this array and input this array into a function, it actually become like this. It's actually like in R5. Yeah, its size of R will be 3 multiplied by 4 because 4 is the integer size in my machine. I mean, there are some cases, I guess, where integer size is not 4, so that's why checking that out using size of can be useful rather than hardcode to 4 number. Okay, so this one, right, we have array and it can decay into this one, the pointer. And let me try to run this, I guess. What is it called? Array in function parameter. Size of array, let's see, this one, right? Size of array 12. And then because of the like what they just said, this is 12 because the array size, the array size take up 4 bytes. So, and we have three, what is it? No, not that one. These three, what is it? 3 elements, right? So 3 times 4, it is 12. That's why this is 12. And the size of parameter, okay, we are entering this one, right? The size of parameter. And it is actually the size of the pointer, not the size of the entire array. So that can be interesting. That can be tricky, I guess, because when we expect to parsing the array, we are only passing a pointer, and this is why we get like this, the length, right? The length of the actual array, it is basically the size of the array, the 12, and we divide that by the size of the, what is it? The type of the element of the array. It is 4. I guess do this to demonstrate that size of in or wait, let me do this 0. Okay, array, right? No, yes. Okay, and then compile this again. Playground array in function, playground array in function. Okay, and then array in function. As we can see in here, this one, the array, the size of array index 0 is actually 4, right? It's also the same as the size of integer, because we are having the array of integer, right? So this is what actually what's going on in this mechanism. We are getting the size of the array, the length of the array, right? And then we divide that by, what is it called? The size of the integer. And that's why we got the, oh, no, to this. Okay, and x. Oh, okay, that looks interesting. We haven't assigned the integer x yet, right? The size of x plus plus, oh, and then print x after. Well, let's find out. Wait. then I can, okay, something like this, right? X equal to, and then printf x okay, something like this. Size of x plus plus. Oh, is this correct? Wait, let me copy this first. Then print x again. Okay, print x again. Wait, something like this. Oh, hello, need learning. Welcome. Alright, let's see what it will print out. Okay, interesting. Says, okay, x equal 4, then x equal 2, wait, what? Oh, this is fascinating. Is there any difference between using plus in here, at the back or the front. Right. I assume it is different with, okay, you know what, to make things easier to understand. Right, let's put it like this, and then the value of x didn't change. Oh, not yet. I'm still not sure why the value of x did not change. Okay. Interesting. Yeah, I mean, this is quite interesting. Wait, and why this is 4? Oh, yeah, because, I mean, the integer, right? Yeah, because size of, okay. Okay. Is the compiler, okay, let me put this, right. Okay, let me hide my webcam first. Okay, wait. Oh no. Okay, why the value of x didn't change? Right, size of is a compiler operation, right? Okay, it just happened at compile time. Okay, it converts the symbol to its size. Terus metadata put all types. Oh, okay. Even at runtime. Okay. Yeah, this is interesting. I mean, I'm still not sure when something evaluate at compile time and also at runtime, right? Okay. So when we use size of this one, wait, let me check this. So when we use size of like this, is the plus x and x plus also evaluate too? I mean, let's assume that we have, what is it called? We have this value. Wait. Okay. Let me do this again. This value, right? Okay. We have this value, which is the maximum integer value. Is it gonna overflow when we use size of? Okay, let me close this again. So, okay. Oh, okay. Compile time. Wait. Compile time when you run GCC. Okay. Runtime equal when we execute the program, the launch process. Okay, when we running the program, right? Okay, because you calculate just convert source code, alright, the C file and the dependency, the binary. Okay. Size of x is just string replacement. Oh, we'll ignore plus. Okay. So even when we put this maximum value of integer, it will actually ignore that. Okay, let's try this out. Right. Okay. I mean, well, if we do this, it will gonna overflow, I assume, right? Right. Oh, interesting. All right. Yeah. We increment first and then give the value. Okay. See, it overflow. Okay, interesting. Yes, size of it. Let me put that in this. Okay. Tim explaining about the compile time, right? Compile time when we run the GCC, the compiler that I'm currently using, and runtime when we execute the program, when we running the program, actually running the program, right? Okay. Convert source code C file into a binary. Okay, a file of machine code, right? Okay, string replacement. So GCC will replace this size of, right, with the, I think, the value of x, the value of x, the value of integer. I mean, I'm not sure how to explain that. We have x with this integer, so it will just print out the value of integer, right? The size of integer. That's why size of an array give you the size of the entire array, because because the compiler stores metadata about arrays. Okay. The compiler stores metadata about arrays, right? When we have pointer that has pointer size, it's just because the compiler stores that metadata about the size. Okay. The compiler stores the metadata about the size. Alright. So, okay. I mean, so when we, what is it called? When we parsing the array into the function parameter, does that mean the compiler see the array as the pointer? I mean, when we are talking like this, this is the context, right? We are passing the array to a function, right? And it will decay into what is it called? It will decay into a pointer. And when we try get the size of the, what is it, of the array, size of parameter, where is it? Oh, this is when we get the size of the array, we get the size of the pointer instead. Is that what happened in the compiler? Alright, I guess that's interesting. Okay. Size of array. Size of, okay. About the size. Okay. So this is actually, so we only know the size of array in the compile time. Is that how it works? Okay, well, let's take a break first. Okay, this is actually interesting. I mean, yeah, like when something processed in the compile time and when something being processed in the runtime, you know. You know the size of every object type array struct variable. Oh, details. I think I've tried that. Oh, read LLF. Okay. Display information about LLF file. We can see the binary file that GCC converts our source code into. Oh. Binary file that GCC converts. Okay, let's find that out. Maybe we will use this array in function as a reference, I guess. Wait, read ALF. What is a min? Oh, all. Okay, we are checking the all information. Playground array in function. Okay. Maybe we should use pager, I guess. Okay. Okay, to complement. Right. Little Indian. What is this? Little Indian. No. Interesting. Yeah, I'm still have no idea what all of this mean. Yet, okay, at some point I might be able to understand what this means. Okay, this is segment section. Little Indian is how your CPU store byte. Oh, the method to store the byte. Oh, does that mean we have another method too? Or is Little Indian stupid? Big Indian is the byte. Oh, the byte order. Okay, so it is different from the two complements. Alright, okay. So the two complement is how our CPU represents negative number, okay. the signed and unsigned, right? Okay, and then the little endian is for the byte order. Is that it? Big endian versus, okay. Big big endian versus, what is it called? Little endian. Okay. Is this the one? Or maybe this one. Wait. Okay. This one, right? Let's see if we can access this. Okay. This is little endian format. 95, 60. Okay. Let me copy this in the chat in case anyone wants to see that. But it's 2 hex nibble. Okay. Alright, 2 hex nibble. So this is the byte 65, 60, AF. Oh, there is one nibble too. Okay. Alright. This is 65, 60, AF 42. Data 1. Oh, okay. Wait. Big endian. This is how. Wait, let me. How data item are placed in memory. Address, okay. Data 1 is stored first and that as a 32-bit. In big endian, the bytes are backward. The compiler needs to generate the byte in the correct order for you. So that is why it is. Okay, wait, let me process this. In big endian, the bytes are backward. The compiler needs to generate the bytes in the correct order. The lowest memory. Okay, but the representation of the memory is still the same between the big endian and the little endian format. Wait, let me put this in the readme to big endian, little endian format. Okay, look at the address. Let's try understanding this. Okay, 95, 60, F42. Oh, so we are saving the 95 hex number. Oh, okay. This is value. Alright. This one is the address 765432210. Okay. So on the address 7, its address of memory has a value. Okay. Its address of the memory have a value. The address 7 have value 95. Oh wait, so this is the okay. I thought this is the memory address or something like that. Okay. The address is 7 and we have the 95 as the value, right? And then address 6, we have 60 as the value. Okay, 60 as the value. Okay, and then 5, we have AF as the value. Okay, and so on. So this is actually the value, not the memory address. Alright, I misunderstood. Okay, and now on this one. Oh, big endian format. Okay, this is the value. So instead of 95, the address 7 saving the 42 value. And then, wait, the address 6 saving. Oh, it is kind of backward, I guess. So instead of left to right, it is right to left. Is that it? The least significant byte out is at the lowest address. Okay, yeah. Alright. Least significant byte. I think what is it called? I encountered that. If we have a number like 1, 2, 3, 4, the most significant digit is 1. Okay. Sample 2%. Base 10. Okay. Right. Let me. Okay, so let me pull out the chat. If we have a number 1, 2, 3, 4, the most significant digit is 1. So let's say if we have 4, 3, 2, 1, the least significant byte is 4. Is that correct? Okay. Interpercent 1000. Okay. Alright. That is most significant. Oh, most significant. Okay, so what is the okay. What is the highest power? So it is still 1 if we have 4, 3, 2, 1. Or 4 is the coefficient of the highest power. So it's the most. 1 is this. Oh, okay. So it is not the order, but the list. Okay. Alright, I think I'm slowly understand. Yeah, I mean, I thought it was just the left side, It turns out that's not the case. Okay. Wait, let me go to the bedroom first. Be right back. Don't forget to drink water. Okay. Oh, yeah, it is left or right side. Okay. Let me pop up the chat again. Okay. In the 4, 3, 2, 1, 1 is the least significant. Okay. Oh, is most significant. It is left or right side. 9 is most significant. 7 is less significant. Excuse me. Okay, it is left or right side. 1 is most significant. 9 is most significant in this one. Okay. Computer architecture book. Okay. Where is it? Computer architecture book. Is this the one? Let me paste this in the chat. Oh, okay. Yeah, I'm planning to read, I think, this one. Programming from the ground up. I'm planning to read this one after finishing off this book, which I rarely take a look. Right? So yeah, one step at a time. Let me copy this in case anyone wants to check that out too. Right, so I'm planning to read this one after finishing this book. I want to try learning C first before going deep into how memory works, how CPU works, all those stuff, right? Because I feel like, well, for example, looking at this, I'm not really sure what's going on, right? And this is because I want to learn C, right? And if I just try learning assembly, then I feel like I might overwhelm. Like, where is this thing used for, Something like that. So that's why I want to learn C first and then trying this out. Yeah, binary can be a bit confusing, but C and assembly or ALF or CPU, they are the same thing. Okay. Yeah, we will get there eventually. But for now, yeah, we are still trying to figure things out. Like, for example, this one, right? Like big endian, little endian. Okay. Alright, see you later. Thanks for coming. Okay. Okay. See you later. Okay. Alright. Let's continue for a bit, I guess. What size of the array? Maybe I should commit this too. And also explain this. This will print out the size of the integer because size of is evaluated in compile time. So, and wait, and the compiler did not evaluate x plus plus or plus plus x. And or maybe something like this, and x plus plus or plus plus x is what is it? Is evaluated in runtime instead of compile time. So the compiler will ignore the plus operation, I guess. Okay, let me add this one. Git commit, okay. Char playground. Add of size of or maybe I should create a new file, for this one. Maybe I should create a new file instead. Playground, what is it called? Size of it. What is it called? Plus operator. That's plus operator. Let's call it that. I'm just bad at naming scheme. Okay. Alright. Wait in main void. Okay, return 0. Include stdio.h. Alright. Okay. Okay, let's reset this. Alright. Let me try compile that just in case. Size of, okay, playground, size of it, plus, okay. It works. Let's commit this. Char playground, right? Add size of it plus operator. plus operator. Okay. This is an example of using plus operator and the equivalent, I guess, like negative, right? Operator. Using plus operator in size of operator. Size of operator, which means that this example show that size of or size of plus x is will evaluated during will print out the size integer. Yes. Will print out the size of integer. Okay, of integer x and not evaluate the x plus plus and plus plus x. This is because size of, let's put this in, because size of operator is evaluated during compile time and the expression how do we explain this? And the expression will be compiled. Oh, I think I think I misunderstood. Okay. In compile time, so we are actually so this happened during compile time, right? That's why the value of x did not change. That's the point, okay? Okay, let me try to explain that here. Value of x did not change because the size of operator is evaluated during compile time. During compile time. And when we run the program, during compile time, and when we run the program, which is different from did not change because the size of operators is evaluated during compile time. And when it is different, different when we run the program, the executable. That's why the value of x did not change because the size of operator is 7. Which happened, okay, I think, which happened before we run the program. That's why when we run the program and print out the value of x, the value of x did not change. Maybe during compile time, right? That's why when we run the program and okay, so why the value of x did not. Is this Vim? Yes, this is Vim. This example shows why the value of x did not change when we use x plus plus or plus x in with size of oh, okay, I forgot about that. Size of operator. The value of x did not change when we use x plus plus or plus plus x with size of operator. Yeah, we are committing the git commit man guess no edit. The value of x did not change. Alright. And then I think we can commit this. Oh, I haven't saved that. My bad. Okay. Playground and what is it called? And what is it? Example of array. Not that one. Add the value. Print out value of Array 0. No, add info about in array in function parameter. Yeah, that's too much. And info array, okay. To make things clearer, that by using size of array means that we are getting the size of the type of the first element of array. There is a lot of in here. And in this case is the size of integer type. Okay, I think something like this, right? And then the one we are trying so hard to understand or at least I'm trying to understand previously, right? Is this one. Okay, wait, is an array of 16 char. Something like let's add this in the reference too. Okay. If we see this, okay. Yeah, I think we should change that to the pointer. Is that it? Where is the 4? This one. Or the memory address. Where is this? Okay. Background case price. Okay. Three, 4, 5, 6, 7, and then 8. Okay. I think using char make things easier to understand because char is 1 byte, right? You can see the increment here. Okay. But yeah. And then 43. This is increment by 5. Also increment again by 5. Okay. After the last element, 1 in address of X. Oh, okay, so I'm trying to learn C. I found this book, right? Basically, I want to learn C, and this book guide us to learn C by building our own Lisp. Lisp is basically another programming language. Where is it? This one, I guess. Lisp is actually another programming language. So you can think of it like something like Python, for example. We can do 1 plus 1 equal 2, right? And what we are building is kind of similar, but the syntax is kind of different. See, this one is Python and this one is what we are building. So I want to learn C by building the interpreter, the Lisp interpreter. And I guess this is the syntax, the Lisp syntax. I mean, I haven't tried Lisp myself, so I'm not really sure about what is right when building the Lisp interpreter. So basically, by reading this book, I kind of learn two programming languages, learning C and also learning Lisp. Kind of. Okay, that's our goal, and well, the goal is learning C, right? So I'm currently trying to understand this challenge, the case place pointer challenge. Let me copy this again in the chat in case anyone wants to take a look, right? So basically we are trying to, what is it? We are trying to understand how this works, right? For example, this one, what will it print? And also this one, x plus 1, what will x plus 1 print, and so on. You need to parse it like plus with, okay, that's the whole point of symbolic expression. Okay. Yep. I mean, in our implementation, by default we assign everything as symbolic expression. So we can do, let's say, this one is actually representing like this one. Again, I'm not sure if that is the correct way of using Lisp, but yeah, for now it is the implementation, the current implementation. Okay, so we are trying to understand this, and this is the tricky one, right? Like what happened, Oh, yeah. I mean, I've been learning this for what? I'm not sure how many hours, but yeah, I've been building this quite a while. So we are on the, what is it? The session, I guess, currently the 86th section. So yeah, it's been a long journey, I guess. I mean, again, the point is to learn C instead of, what is it called? Instead of reading lips, reading the proper lips, you know. So yeah, I've been going on my own rather than finishing this book, if that makes sense. So okay, by adding this one, right, size of the array, for example, when we have the array of 5 not integer, I guess, character, right, we will have the value of by 5 of 5 character size. How do we get that? With size of operator. Getting the size with the size of operator. Okay, by 5 character size. Operator, I guess. Integer, okay. I mean, in this example, they are using integer, right? But in my example, I feel like using char make it easier to understand, you know. Like if you take a look at this, A3, A4, and so on until A7, and then when we add 1, it become A8. I guess we can also add this one. Right. Plus 2, right, and then 6. Plus 2, 6. And then let's compile again. Playground, guest space, pointer challenge. Okay. This is when we're adding 1, right? Should we like adding the char? Like spirit is put char. Okay. Background case please. Okay. Right. This is the memory address. Okay, and then we plus 1 because we have the array with 5 elements, right? When we plus 1, we are actually adding the another 5 element to the array. So it print out this, what is it called? This memory address. And then if we add plus 2, well, it become harder to see, I guess. We are actually adding another 5 element. I think this represents what's going on. Let's say we have memory address of this one, the address of X, is 001, right? And we would have 1 byte of array element. The representation would be like this: 001 until 005, right? I mean, it is kind of similar to this one. T3, wait, T3, T4, T5, T6, T7. We can also represent this like this one: 001, 005 until 005, okay. And then, oh, or maybe, no, not 005, but 004, right? 3, 4, 5, 6, 7. Interesting. Okay, and then this one is 5. 0, 1, 2, 3, 4. Should be 0. Well, anyway, we're adding 5. 1 element, okay. Oh, right. This is, I guess, 4. This is 1 byte, and then 2 byte, 3, 4. No. I think it's like this one, right? 1 to 5, and then 6 to 11, 12 to 17. Okay. That's basically it. I'm trying to analyze that, what's going on. Guess. Okay. Oh, right, it's not 6, but it should be, what is it called? I think 10, right? Where is it? This one. Oh, background. Alright, it's the same. So adding 5, and then another 5, and then another 5. That's basically what's happening. Let me commit that first. Git commit your playground. Change to from into char, because char is 1 byte on my system. I feel like it's easier to understand if we use char type instead of int type. Instead of int type. For this example, okay. For this example, also add an explanation what happened when we do 1 or plus 2. X plus 2. It's basically when we use it means we use the entire array in that array and not the what is it called, and not only the first element of the array. That's why, and when we add 1, I think this is apply, right? And because of that, wait, oh right, I also want to read about this. Well, let's do that in the next session, I guess. And because of that, we have when we do plus 1, we are actually adding one element after the end of x, the end of x array. In this case is after element 5, after the 5 elements. This can be number plus number multiply sets of because we are using pointer, because we are using I guess pointer in expression x plus 1, right? We are actually doing pointer arithmetic. Doing pointer arithmetics. Which we make take a look right. We'll take a look later. this commit is to understand, right, what's going on between this and this one. Another 5 char is actually the same as index 10 of the array, which does not exist supposedly, right? Okay, we have that one. Git push. Okay. Alright, in case anyone new, you can check that in my GitHub repo. I'll post this in the chat for those who just joined. Okay, I think we will continue this one on the next session. Alright, that's it for now. See you next time. Bye bye.